Hi everyone. In this presentation, I will speak about nanodots decorated MIM semi-ring resonator cavity for biochemical sensing applications. My name is Alibert and I am with Samara National Research University, Russia. This paper is co-authored by Sergey Fomkenchov from Samara National Research University and Hen Hong Mai from VNU University of Science, Vietnam. Surface plasmon polytron are optical waves emerging from incident photons coupled with free electrons on the metal surface. The E field intensity of surface plasmon polytron is strongly bound along the metal dielectric interface and decays drastically in the direction vertical to the interface. A wide range of surface plasmon polytron based waveguides are reported. For example, striped waveguide, semiconductor insulator semiconductor waveguide, metal insulator metal waveguide, nanowires and groove waveguides among others. Among these, the metal insulator metal waveguide is the most extensively used plasmonic based nanostructure for the realization of integrated optical circuits. MIM waveguides are plasmonic structures in which an insulator is enclosed by two metal claddings. The straightforward design and capability of these waveguides to confine light at the sub-wavelength level are the key features of this system. To realize highly integrated optical circuits, researchers have conducted rigorous research on the design of these devices using MIM waveguides. These devices include filters, sensor, switches, couplers, splitters, demultiplexer, and demodulators, among others. Refractive index sensors have many uses in the biological and chemical fields and have been intensively researched in recent years, such as the concentration of the solution and pH values that can be calculated by changes in the refractive index. An electromagnetic field is generated by exciting the device by the use of a light that produces surface plasmon that are highly concentrated on the metal surface. When a substance under consideration is brought into contact with the sensor, the effective refractive index of the MIM waveguide changes, and as a result, the redshift of the resonance wavelength is observed. Surface plasmons are very sensitive to the changes in the refractive index in the close proximity of the surface. Changes in refractive index can be determined, for example, the changes in the resonance wavelength, intensity, or phase in one of the characteristics of light coupled to the surface plasmon. In this paper, a relatively simple and novel sensor design is presented, which consists of a semi-ring cavity side coupled by a MIM bus waveguide. The cavity is loaded with nanodots, which helps in the amplification of the resonant surface plasmon polytron modes. As a result, the light matter interaction enhances and offers a highly sensitive design for the detection of slight changes in the refractive index in the ambient medium. In this slide, you can see the schematic of a MIM semi-ring resonator design. In figure A, the standard semi-ring design is shown, whereas the nanodots loaded semi-ring resonator is shown in figure B. The geometric parameters of the sensor designs are capital L, W, R1, R, and D, which represents the length of the bus waveguide, the width of the bus waveguide, the width of the semi-ring cavity, radius of the semi-ring, and distance between the bus waveguide and the semi-ring respectively. For nanodots decorated design, the radius of nanodots is represented by capital NDR, which is varied from 5 to 24 nanometers in order to calculate the total electric energy in the cavity. The geometric parameters used in this study are shown in the yellow box. A finite element method FEM is used to simulate the transmission spectrum and E-field distribution using a commercially available software, COMSOL. The subdomains in the sensor design are divided into triangular mesh elements with a fine mesh grid size, which helps in obtaining accurate simulation results with the available computational resources. It is ideal to design an open boundaried domain, that is a limit of the calculation domain where the electromagnetic wave moves without any reflection when solving electromagnetic wave problems. Scattering boundary conditions SPC are used at the outer edges of the FEM simulation window to approximate an open geometry. The structural parameters of the proposed sensor designs can influence the resonance spectrum. The impact on the transmission properties of the geometric parameters is therefore investigated. The metal and insulator materials used in this work are gold and air, respectively. Gold is desired as the metal layer due to its biocompatibility and resistance to oxidation compared to silver. The refractive index of gold is calculated from the Drude-Lorentz model as shown in the slide. The TM mode of the MIM bus waveguide is excited by a plane wave at the input port. As the width of the waveguide is much smaller than the incident light, so only fundamental TM mode exists. The dispersion relationship of this fundamental mode is shown in the slide. In this slide, figure 1 shows the on-resonance and off-resonance E-field distribution in the standard and nanodots loaded sensor design. When the standard sensor design is simulated for the visible and near-infrared wavelength ranges, two resonance dips are obtained. The field power of the resonance wavelength can be tuned by rotating the semi-ring along the normal axis as shown in figure 2. The angle theta is varied between 0 and 90 degree. As a result, different surface plasmon mode powers coupled to the cavity is obtained. The maximum resonant mode power is obtained at theta is equal to 10. The normalized transmission of the standard MIM semi-ring resonator design at theta is equal to 10 is shown in figure 3a, where resonance dips are obtained at 632 nanometer and 832 nanometer. Resonating wavelength has a direct relationship with the length of the cavity as shown in figure 3b, while considering the resonance dip in the visible spectrum, that is lambda resonance is equal to 638 nanometers. Interestingly, this proportional relationship between lambda and R can provide guidelines to design a sensor of suitable dimensions of the resonant cavity for obtaining sharp Lorentzian dip in any desired wavelength range of choice. In general, ring resonators are responsive to ambient refractive index and their resonance wavelength manifests redshift with increasing refractive index. The spectral response of the sensor is determined by filling the ambient medium with refractive index values which lies in the biochemical domain. The normalized transmission spectrum of the standard sensor design is shown in figure 1a, whereas the normalized transmission spectrum of MIM semi-ring cavity resonator design having 11 nanodots of radius 15 nanometer is plotted in figure 1b for visible and near infrared wavelength range. The transmission spectrum is calculated at n is equal to 1.0, 1.34 till 1.38 with a step size of 0.01. Sensitivity has a direct relationship with the size and number of nanodots. We plotted the total electric energy of surface plasmon polytron in the MIM waveguide semi-ring cavity. In the standard semi-ring design, the total electric energy is quite low, which enhances when the nanodots are arranged in the cavity. In this work, we have used 11 nanodots periodically arranged in the cavity. The total number of nanodots is dependent on the size of the cavity. As the radius of nanodots increases, the total electric energy of surface plasmon polytron intensifies, which offers a better light-matter interaction. Here, we will discuss three significant factors which are used to estimate the sensing performance of the sensors, such as sensitivity, the figure of merits, and quality factor. The sensitivity is used to determine the sensing performances of the sensor, and it is expressed as S is equal to delta lambda by delta n, where delta lambda is the resonance wavelength shift due to the refractive index variation in the ambient medium. Typically, the figure of merit FoM is used to further evaluate the sensing performance of a sensor, and it is expressed as FoM is equal to S over FWHM, where FWHM is the full width at half maximum. As a sensor, both high S and high FoM are required in order to ensure good optical resolution performance. Much research has been done to enhance S, but longer wavelengths are always affected by wider FWHM, resulting in lower FOM. In addition, FWHM is connected to the lifetime of surface plasmon, which usually regulates the sharpness of the peak. Perhaps the FOM is the most generic metric for comparing the performance of plasmonic platforms. Last but not the least, the quality factor is defined as lambda resonance by FWHM. The sensitivity of standard cavity resonator and nanodots embedded cavity resonator design is shown in the figure. The standard design offers a sensitivity of 600 nanometer per RIU, whereas the sensitivity of nanodots embedded cavity enhances due to the amplification of surface plasmon polytrons, which results in better light-matter interaction. The sensitivity of cavity loaded with 15 nanometer radius nanodot is around 805.88 nanometer per RIU, which is further improved to 1084.21 nanometer RIU by increasing the nanodot size to 24 nanometer. However, squeezing the confinement area of surface plasmon polytron leads to higher FWHM, resulting in lower FOM and FWHM as shown in the table. Here shows the sensitivity comparison table of previously reported plasmonic sensors having different cavity designs such as T-shaped MIM waveguide, ring cavity, grooves cavity, double-sided couple square ring resonator, stub coupled square cavity, among others. The majority of the sensors exhibit a sensitivity in the range of 636 to 938 nanometer per refractive index unit. However, our proposed sensor design having nanodots of 24 nanometer radius can offer a sensitivity of 1084.21 nanometer per refractive index unit, which is comparatively higher than most of the previously reported studies. To conclude this paper, I must say that we have presented a numerical study of a novel design of a highly sensitive plasmonic sensor based on a semi-ring cavity. The spectral characteristics and electric field distributions are studied using the finite element method. The standard sensor design shows a reasonable sensitivity of 600 nanometer per refractive index unit, which can be further enhanced by decorating nanodots in the cavity. The radius of nanodots plays an important role in the amplification of surface plasmon polytrons in the cavity. It is shown that the total electric energy in the cavity enhances with the increase in the radius of the nanodots. Therefore, the nanodots decorated semi-ring cavity design can offer a sensitivity, FOM and Q-factor of 1084 nanometer per RIU, 57 and 59.57 respectively. The proposed sensor design shows great potential for nanophotonics applications. If you have any question regarding this presentation, please feel free to contact me on this email provided in this slide. Thank you very much for your attention.